Welcome back to the aromatic substitution reaction chapter. Today we're going to be talking about the spectrum of deactivation and activation. We're first going to look at activation. Alright, so you can have either a weak, a mild, or a strong activator. And this will tell you how directing that molecule is. How much of an effect is that activator going to be? So it can do that orthopara directionality. So strong activator groups are going to exhibit lots of, we'll just say directionality so we don't have to write orthopara a lot of times. So these groups show lots of directionality. Same with strong deactivators. They show uniquely their own strong directionality. However, if we look at weak ones, these show less than the other ones. They will still show it to a good degree, just not as good as, say, a strong variant of either a deactivator or an activator. So less directionality. Wow, my handwriting is terrible. So hopefully you can make out that says directionality. I can't even make it out, and I'm the one writing it. So, okay, so how do we classify strong, mild, and weak activators? Let's start with strong. So to be a strong activator, you have to have a set of lone pairs and nothing else. So a good example is, I'll just draw, this here is hydroxide. A hydroxy group, right? We know that on this molecule it will have two lone pairs that it can donate, right? And that would be an example of a strong activator. We can kind of see the difference here when we start to look at mild. A mild activator has lone pairs, but it's already in conjugation with something. So an example would be this group here. So if we had an ester, for example, that would be an example of a mild activator. Now, while it can donate here, these electrons are being pushed this way, right? So it kind of lowers the energy of these electrons right here, right? It's going to lower that energy, and that's why they're mild, right? It's less activating than strong. Okay. Now, for what we've been all been waiting for, we're going to do weak. So a weak activator is one that donates electron density through hyperconjugation. And we saw these with, for example, alkyl groups. So if I was to say add a methyl group here, we know that through hyperconjugation, i.e., if I were to just draw this out here, there's a good video on YouTube that explains hyperconjugation. It's kind of hard to see without a visual, right? So if I drew this carbon atom here, let's say this is part of the aromatic compound. It has an orbital here, right? And then let's draw our group here, our methyl group. And we'll draw one of the hydrogen orbitals here, right? We know that some of these electrons through hyperconjugation are going to make its way over to this orbital just by chance, right? And that's added stability to the molecule, right? It's going to donate electronic charge, and that is an activator. Even though it's weak, it's very, very, very slight, but it's still there. So we consider this a very weak activator. And to honor that, I'll draw the smallest dipole arrow I can. So, yeah, very, very, very small. All right, so now let's get into deactivating groups. And we're going to go in reverse. We started with strong, went to mild or weak in our activators. Now I want to go in the reverse direction here. So we're going to start with weak. Weak deactivators. Weak deactivators are ones that compete with induction and resonance stabilization of an aromatic compound. So for example, we saw this with the halogen exception. Very, very weak deactivator. All right, now let's go to mild. A mild deactivator is any group that has one electronegative atom that's pulling electron density from the ring. So an example of this would be if we had a ketone. And I'll draw like if this is our group here, we're going to draw that carbon and then the oxygen. And we know it's withdrawing electron density, right? Because if we have, let's say, a pi bond here, I know this isn't to scale, but let's just say this is an aromatic pi bond, it's going to do this here, right? We all know it's an electron withdrawing group because of that resonance structure right there. It's pulling electron density from the ring, so, and therefore it is a mild deactivator. Now, our strong deactivators are kind of hard to categorize, but they're quite simple once you get the hang of it. Just think multiple electron withdrawing electronegative atoms. So here we had one atom that's electronegative, that's pulling electron density from the aromatic ring. But here we have two. And a prime example of this is NO2. So if we have this here, now we know through resonance it could put a negative charge here or a negative charge here. And for that fact alone, just because we have two factors at play pulling electron density from that ring, it's going to be what we call a strong deactivator. And like we said, our strong deactivators are going to be stronger deactivators than the mild ones, and the mild are going to be more strong than the weak deactivators. That was the spectrum of activating and deactivating groups. Hopefully you guys can pick up on the trend there, and I hope you guys learned a lot. Have a wonderful day and make sure to check out the next video.